So back well, actually in week 3, but our week 2 schedule for section is as follows. So first one, again, we're going to review the class materials we learned in last week. That is the Bohr Model and the Broglie wavelength uncertainty principle, and cover some of it we talk about today, which is operator, the part, okay? And only part 1. We'll have a formal discussion about operators in chapter 4 and also in later chapter 3. So this first one, Bohr Model, I think this is pretty important in chapter 1, and you can tell today's quiz actually will give you one question related to this. And hopefully some of you have worked out that question. Okay. So where does Bohr's model come from? So it actually comes from the atomic emission spectrum, and it's figured for hydrogen atoms. I don't know whether you still remember that in Chem 1M, the Gene Chem lab, in lab 5, you actually observed this image, right, this picture. And at that time, we told you, this picture showed you the energy level of the hydrogen atoms are actually not consecutive. It's concrete, but it's discrete. So it's quantized energy level if you quantize the transition energy and reflect on the spectrum at different lines. But at that time, we only talk about that. And also you learned some in Chem 1B, talk about the energy levels, and actually can perfectly expand this spectrum. And that actually is the key part of Bohr Model. So within this class, we'll have a formal discussion about that. And this is exactly the picture you learned in Gene Chem for Bohr's model to explain the hydrogen atoms with 1 electron, 1 nucleus, and with several orbitals, right? And based on this model, it actually contains some key assumptions, which is actually the key part of Bohr's model. And the first assumption is we have discrete and stable orbitals for electrons to move. As you can see, I labeled 1, 2, 3, 4. Those are stable electron orbitals. And we can also calculate the energy of each orbitals using this equation. And the first thing I want you to pay attention is the negative sign. Actually, the energy is actually negative. I mean the absolute energy of the orbital. So negative energy means stable, right? If you have a positive energy, you're actually energetic. It's not stable. And some terms I want to explain. The first one is the mu here. So in chapter 1, meaning our textbook, we do not use the reduced mass. We just use the mass of the nucleus. Because the mass of the electron is quite small compared to the nucleus. But anyway, to form a more accurate picture, we need to use reduced mass, which is denoted as mu, and can be calculated by this. Okay. M1 stands for the mass of the nucleus, M2 stands for the mass of the electron. And the second one is here, the quantum number. Okay. So N we call actually the orbital number. Or actually from Chem 1B, you learned this is called the principal quantum number. And that quantum number, so they can just be integers from 1 to infinity. And not include 0. Okay? So this is the first key assumption. So based on that, we actually can label each orbital with 1, 2, 3, 4, 5. And actually in later chapters, we will see this one is actually 1s, 2s, 2p. But here we can just label as 1, 2, 3, 4, 5 based on the quantum number. Okay? This is the first most important assumption. And followed by that is the second assumption, which related to linear momentum. So electrons, imagine, they can move within the orbital with a certain speed, within a certain direction. And also you can measure the distance between the electron and the nucleus. Denoted as R, and we know the linear momentum is defined as this. And Bohr believed linear momentum, the magnitude, we know linear momentum is a vector, right? But the magnitude of linear momentum is actually quantized. Okay. N times h bar. H bar is called reduced Planck constant, is h over 2I. Okay. Anyway, this seems not that important for chapter 1. But actually, from here, we can derive a very important conclusion to describe hydrogen atoms in chapter 7. So in chapter 7, we will come back to this conclusion and we will see why this is important. But from here, we can hardly appreciate the importance for this assumption. The third one actually we can make a lot of questions based on this, is the transition between two energy levels. So for example, electrons can be promoted from n equals 1 to n equals 2. And once the electron is jumping or promoting between the two different energy levels, it involves energy change. And based on Bohr's model, the energy change can be calculated by the Bohr equation. Okay, and Bohr equation includes one constant called Rydberg constant. Okay, so don't confuse with those names. Okay, this equation comes from Bohr model and it's called a Bohr equation, but it contains a constant called Rydberg constant. And the Rydberg constant is actually for a general atoms. It's not only hydrogen atoms can be expressed as this with Z as the atomic number. But in chapter 1, we mainly talk about hydrogen atoms, which that means Z equals 1. And if we plug in Z equals 1, we plug in other constants, and we calculate the reduced mass, and we can get this number. This is the famous Rydberg constant we give to you. You can directly use in the homeworks or in quizzle exams. Okay. But pay attention. As you can see, Rydberg constant, I use a subscript H to represent this constant is just for hydrogen atoms, where Z equals 1. If for helium atoms or other atoms, pay attention to change Z to other numbers. Okay? You have a question?
Okay.
Yeah, that's the thing. So do not assume the Rydberg constant is always this number. Keep in mind this number only for hydrogen. If you have a helium, you actually double it, right? Okay. So those are the three key assumptions. Any questions about this? Based on that, this actually can describe a somewhat complete pictures for Bohr's model. So let's take a closer look at it. And when we calculate the delta E, depends on the number of Ni here means the initial, Nf means final. So it depends on the initial quantum number or the orbital number and the final orbital number to decide actually the sign of delta E. Right, think about that. If we plug in n, let's say Ni equals 1, Nj equals 2, how will the sign be for the delta E? What is the sign for delta E in that case? From 1 to 2. We will plug in 1 minus 1 over 4, right? It's positive. So positive means the energy is absorbed by the atoms to promote the electron. So in either case, if Ni equals 2, Nf equals 1 means from 2 to 1, what's the sign for delta E? It's negative. Negative means we emit the energy. That's the truth, right? Because the electrons coming from a higher energy level, when we go back to the lower energy level, it emits the energy of light and the radiation. So here I want to emphasize it here. Sometimes when you do the calculation, you get a positive number, and then that just means it absorbs the energy. But if you get a negative number, this means the atom emits energy. Okay, so the sign, the meaning of the sign for the I is actually here. But when you need to convert the energy to wavelengths, to wave number, you don't need to care about the sign. You just choose the absolute value. Okay. All right, so a more accurate energy level picture for Bohr model, actually you can calculate it based on the energy level equation I showed before. So for n equals 1, you can plug in n equals 1, and you calculate all the things, and you convert the energy into the unit of electron volts. So I didn't label it here. So here should be En with the energy of electron volts. Okay. And you will get the first one, when you plug in n equals 1, you get this number. N equals 2, n equals 3, 4, until infinity. When you plug in n equals infinity, you actually 1 over infinity equals 0. So the last one will be 0. Okay. And each number, actually, you will see the space getting smaller and smaller. This is not derived by something else, just from the mathematical expression. Once you plug in n equals 1, you get a different number. You get a number here, n equals 2, you get a different number. And you can calculate the distance or the space between the two. And you will find, actually, the first space will be larger than the second space, and the second space will be larger than the third space. So it actually forms like this picture. The energy level. It's not an equally spaced energy level. It's something like that. Okay. Any question about this? But somewhat hard to understand. But anyway, if you understand the mechanism behind, how can I draw the picture? And, you know that. Okay. So this level here, I told you, when n equals infinity, you plug in, you get 0. We call this as vacuum level. Possibly you heard from Lincoln class as well. That means if the energy is higher than vacuum level, you actually ionize the atom. But anyway, we don't need to pay attention right now. We just pay attention to the atom itself. Okay. So below the vacuum level, we can have some transitions, right? That one electron, if this is hydrogen atom, that one electron can transit between different energy levels. And I have several transitions, but I want to group as this way. We group all the transitions according to their final energy levels. Okay, according to the final energy levels. So the first one, I say, if any electrons transition from a higher energy level back to n equals 2. Then if we write out all the energy levels like this. Okay? So all the electrons from all other energy levels which is higher than 2, jumping back to n equals 2. And you get this picture. And so you can calculate actually the energy difference between this 2 and this 2 and this 2, right? And you can convert to wavelengths. And trust me, for the first transition, you calculate the energy, you convert to wavelengths. The wavelengths is exactly forcing to the red light region, which is the red visible light. So that means the transition from here to here will give you red light radiation, and you will see red light. And for this one, we know the energy gap actually becomes larger, so the wavelengths will become shorter or longer. Will become shorter, so the color will shift to blue or shift to red. Shift to blue, so the second one will be green light. The third one will be blue light. The fourth one will be the purple light. And the fifth one and more, they force into UV light, at which you cannot see it. So if we use a spectrometer to detect all the transitions within what's called Bohr series. So Bohr series defined as final quantum state equals 2. Now we will get this picture. So first line, this transition give you this line. This transition give you this line. This transition, this line. This transition, this line. And what's more, they are UV region, we cannot detect it. You get the picture? So that's why we only observe 4 lines in atomic hydrogen emission spectrum. Because we can only detect the visible light. For other UV light, we use some special techniques. But at that time, when the scientist, the Balmer, did the research, he could only observe the visible light. So that's why he concluded his Balmer equations completely based on the visible light. Okay? So we have the final state n equals 2. So we must have some final state n equals 1, final state n equals 3, n equals 4. So we have different names. Okay? For the first one, when all the transitions from still other transition energy levels to n equals 1 to the ground level, we also give those group of transition a name. That is called, have you read the book? Finite theories. N final equals 1. Okay, N final equals 1. For this one, I use the dot line or the dashed line for the transitions. This is simply because all those transitions will give you UV light. So why is UV light? Think about the energy gap here is actually larger than this one. So larger energy gap means smaller wavelengths or longer wavelengths. Shorter wavelengths. So shifted to blue or shifted to red? Shifted to blue. Blue shifted to UV region. So if this one is actually UV region, this one must be UV region. This one will be higher and higher energy, will be lower wavelengths. And this will be far UV. Okay? So all those transitions with our spectrometers, we only use visible light, we cannot detect it. So the same for n equals 1. And how about n equals 3 if the final state? If n equals 3, we also give a name. All those transitions. Last series. That's the one we asked you to calculate. Paschen series. passing series, and final equals 3. But in this case, you will see the first one, the transition, will give you an energy much smaller than this transition, right? So the wavelength will be longer or shorter? Will be longer. Longer will shift to which region? Red region. So actually this one falls into IR region, the infrared, which we could not detect. Okay, so this one is IR, all the IR. But I have one more question. Let's say for all the Bohr series, which transition will give you the longest wavelength for all the Bohr series? From n equals 1 to n equals 2. The longest wavelength means the lowest energy. The lowest energy means the energy gap is the smallest. So from n equals 3 to 2. N final equals 2 is based on the definition. N equals 3 is based on the longest wavelength. Get the picture? So this equation I showed last time is really important. For all the things, and also the correspondence to the color. Okay, they are quite important. Always keep in mind, energy is inversely proportional to wavelengths. It's directly proportional to frequency. It's directly proportional to wave number, which I will explain later about this. Okay. All right, any question about this transition? Again, highly important. We had a question in the quiz. We may have another question in the exam. Okay. And the last point I want to mention within this energy diagram is this case. So if we promote one electron from whatever energy level to the energy level which is higher than vacuum level, we call this process at what? Above vacuum level, actually, it's not an atom anymore. We separated the electron with the atoms. That is called ionization, exactly. So the energy which you need to promote, let's say n equals 1 electron, to just the vacuum level. So the energy which you need to promote the electron from here just and to right to the vacuum level. The energy gap you can calculate. This is called ionization energy for n equals 1. So as you can see, we have different ionization energy for different orbitals. Right? We can have ionization energy for n equals 2, which means the energy between here and the vacuum level. N equals 3, ionization energy is here to vacuum level. And how can you calculate the energy? You base on here or you base on this equation. You plug in different Ni or Nf and use the Bohr equation. Okay? So let's talk about the quiz today. The quiz asks you to calculate what's the wavelength for this line. Okay? And this line is within the partition theory. So based on that, I know everybody you want to know, you know how to do that by using their IED code, because this is hydrogen atoms. So most of you can write on this and choose the right equation. But the problem is which number I should plug in here and plug in here, right? So after today's section, can you tell me the first one? Nf equals what? Nf equals, this is what series. The partition series Nf equals 3. What is Ni? Well, Ni is, think about that. Ni is the first one. There's a long line, right? So within the whole set of transitions, they are all defined as passing series. And this is kind of a shorter wavelengths. This must be longer wavelengths. Or in other words, this line corresponds to the longest wavelength transition within partition series. Good idea?
I may be wrong, but I think you have your Ni and Nf switched. I think Ni should be 3 because that's the start of the passion series, and then.
Oh, not matter. You just then change the sign.
Right.
But when we calculate wavelengths, we choose the absolute value.
Right.
So that doesn't matter. Okay, I know what you're talking about. But just think about it. So anyway, the more important thing is this slide corresponds to the longest wavelength transition in partition series. Do you agree with me? why this is the longest? Based on this, here is shorter wavelength, this getting longer, this one must be the longest one. And we know all the series here, they are partial series, so this one must be the longest transition, longest wavelength transition. So that is from n equals 1 to n equals 3. Well, think about that. N equals 3 here. If from infinity, energy gap is about this. But we want longest wavelength means the smallest inner gap. Okay then? So you plug in n equals 4. Use this equation, you plug in, do you get that number? And actually, this number is covered by the professor. This is actually a picture directly copied from the textbook. And the textbook is 1876.0 nanometer. Okay. So, the importance of reading the textbook. Okay. All right, any questions about this? I know a little bit hard to understand, but all the things we play the trick is about the inners, the relationship between inners, wavelengths, frequency, wave number, and the picture. Okay, all the things like this. Okay? So if no other questions, I want to emphasize here that the last of this part, Bohr model is not a perfect model. It still has several drawbacks. Okay? The first one is Bohr did not explain why we have stable electron orbitals. So why the orbitals are stable there? You just propose, we have stable electron orbitals, and we know the inners. But why the orbital are there? Why they are stable? No explanation at all. Second one, it is unable to expand some other emission spectrum of atoms, not the same as hydrogen atoms. Simply means with many electron atoms. Even for helium with 2 electrons, the Bohr model cannot expand. It's totally deviate from the experimental result. Okay? But it only works for hydrogen or something we call hydrogen-like atoms. So hydrogen-like atoms means the atoms only have 1 electron, single electron atom. So this could be hydrogen, right? And could be what? Some ionized atoms like helium plus, lithium 2 plus. They are hydrogen-like atoms, and they can be somewhat expanded by the Bohr model. But for more complicated, even though for hydrogen-like atoms, Bohr model will expand that. Okay? It's the second drawback. After this represents after the whole theory is not complete, is not perfect. And the third one, even worse, is it is unable to expand the fine structure of hydrogen atom emission spectrum. What it means fine structure I mean here. So this is the spectrum of the hydrogen atom emission. So if we take a close look at each one line, the single line here, if we have a very accurate detector, we actually can detect 2 lines with a very small space. So this is not a single line, this is actually 2 lines here. But based on Bohr's model, there's only 1 transition and give you 1 line. There are not 2 transitions. So how can you extend this? Okay, so clearly, this Bohr model is not perfect. So keep in mind, and we will come back to address this issue in chapter 7 when we talk about the real hydrogen atom picture using quantum mechanics. Okay. So next, any question about this part? If not, we'll go to the next section, next part about the Broglie wavelengths, or the Broglie wave is actually a lighter topic than Bohr model. So the Broglie wave theory comes from the explanation about the origin of light. Actually, there's a debate, but actually in some of the literatures, like in Greek mythology, we know that Greek mythology believes the light comes from. Where is the light from? Have you read about that? The Prometheus who stole the light from the Mount of Olympus and passed it to the human. Okay. But anyway, have you read about the Bible? Some of you have believed, if you have some religious beliefs, you have read the Bible. And in the Bible, we explain the origin of light as the God. So if God says that there be light, and there's light. I don't know why. Okay. Have you ever carefully observed the seal of UC system? The University of California and the seal? There's barely light. Okay. But anyway, those are some religious stuff. Let's get rid of them and let's come back to science. Okay. In real science, there's a debate that lasts for about several centuries about the origin of light. So the first one is Newton proposed that the light is composed of corpuscles. So corpuscles is defined as small particles. So based on that, Newton successfully explained the reflection of the light. So we have used the mirror, and the light hits the mirror and reflects back. So if we think about all the light that made of corpuscles or the small particles, when the particles hit on the mirror and then bounce back, that's natural. Okay. So this one, Newton proposed that. But another one, scientist called the Huygens proposed another theory. It's called the wave theory. So based on that, you think light is just a wave and it can diffract. Because at that time, people observed the diffraction of light. So if we think the light is made of particles, how can the light diffract? Right? We have some the diffractions. A simple picture is the light hitting on some barriers is actually someone goes through have a diffraction pattern. So if this is a particle, how can it be true? So instead, if we propose light is line, these waves, actually we can propose, we can actually successfully explain the diffraction and also the refraction. So based on that, we call this one. Newton is actually the leader of the group called the particle group or particle team, and the Huygens is the leader of the wave team, and they kind of debate with each other or they compete with each other. They want to know, they want to persuade others. So the first progress made is within the wave team, which I believe you have heard about this, the Thomas Young double slit experiment, and show the clear pattern of diffraction pattern of the light through the two slits. So this clearly indicates that light is made of wave, right? So the wave can diffract. Okay, this is the first progress. And the second progress made is actually between the two teams, where they focus on a thing called the Poisson dot, or the Poisson point. So this story is related to two scientists at that time. So one is Poisson, another one is his student for the first time. And Poisson actually is a member from the particle team, and he did not believe light is made of waves. So he assumed light is wave. So first he assumed the light is wave, and then he did the calculation for some cases. For a case like we have a small barrier here, and the light hit on the barrier, and we calculate what we will get if we put a screen backwards the barrier. Okay, based on the Poisson's calculation, he got to the conclusion that we will see a bright dot right behind the barrier here. So that means here this is front. And used the assumption of light is wave. So Poisson strongly believed that this was ridiculous, because he believed the light is particle, and particle must be bounced back and cannot even reach here. So he actually asked the interesting is his student believed light is wave. And the worst situation is Poisson is in the research committee of personnel. So in graduate study, we've defined the research committee is actually the ones who decide whether you can graduate or not. So Poisson told his students, if you want to graduate, please show me you can get a bright dot here. So Fresnel took this challenge and did many experiments, and one day finally he found one. We can observe actually the bright dot. So this is fun. This is actually fun because since we observe the bright dot here, that simply means all the calculations based on the assumption that light is wave is correct. Right? Because by only assuming that light is wave, we can get the bright dot, and the experimental observation is we can get the bright dot. So again, the particle team actually lost in this round. Okay. So round 3, well, actually round 2, the wave team won again. and then come to round 3. Progress made, again, within wave t, where the famous scientist Maxwell developed a whole set of equations that can successfully explain the wave-like behavior of the light using the electromagnetic theories. And this is so perfect equation set that everybody believes this is the end of the debate. Well, that's what happened before 1900. And I emphasized last time, 1900 is the birth of quantum mechanics. And you still remember him? Einstein explained the photoelectric effect by assuming that light is made of photon. Again, particle team won this time. Well, here comes the thing. We have light that behaves as a wave, light behaves as a particle. So what's the true picture? So guess what's the ending of this story? The analogy. Stop arguing, you are both correct. So de Broglie united the two teams together and resulted in the de Broglie wavelength theory. So in 1923, de Broglie proposed that matters display both particle-like behavior and wave-like behavior when moving. It's not only light, but other stuff, all the things, including ourselves. So if I move, I'm a particle and I'm also a wave. And the wavelengths, so if you see the matter display wave-like behavior, you need to show the wavelengths. Okay, what's the wavelengths? So the wavelengths can be calculated based on this equation. Lambda over h, lambda over p, and p is the momentum. This is the equation shown in your textbook. But I don't think that's enough. I extend the equation a little bit. So the first extension is to express p equals mv. Well, that's for sure. But the second extension, I don't think many of you know that. Okay, this is actually pretty important. You can, again, express kinetic energy, express the momentum using kinetic energy. Okay, so P actually equals square root 2MEK. And you can just use this one. So remember in your homework program, we give you a question which gives you the kinetic energy, right? So once we give you kinetic energy, how can you calculate the wavelength? Just use this equation. So it's faster than you to derive all this, and then you first solve the V, and then you solve the kinetic energy. Okay, it's faster. So you directly solve the two. All right. So why this equation shows the particle-wave duality of the particle? Because the first term here, wavelength, actually shows you the wave-like behavior, and the momentum, of course, is the particle. Okay. So simply, this means for any matters, if it's moving, this equation holds true for them. So your matter displays wave-like behavior and particle-like behavior together. So all together, they're within one thing. So I cannot use the exact picture to show you what this looks like, but I can use some approximation like this. There are two persons in there, and the aggregates together, which you cannot tell. Somewhat. Okay, somewhat you cannot tell. So this is something like that. So pretty hard to imagine. In microscopic world, for a particle, when it's moving, it moves like a wave and also like the particle. So something like that, pretty weird. Okay. So I guess you are thinking about why can't we perceive our own wave-like behavior? Right? I asked you to heat the wall. We must heat the wall. We cannot diffract and just go through the wall, right? So what happened to ourselves? According to de Broglie wavelength or wave theory, we will still behave like a wave. But why can't we diffract something? So this is close to the critical condition for diffraction to be observed. The critical condition is your de Broglie wavelength should be comparable to the barrier size. Okay. So they say the wall is about this long. So in order to diffract through the wall, your de Broglie wavelength should also be comparable to this length. Okay, or through the length. So let's see what happened. I'll give you two examples. So one is a pitch ball. So it's not even yourself, it's with a much smaller math. And I'll give you the velocity, and actually you can use lambda equals h over p, and you can calculate the de Broglie wavelength, right? I will give you this number, 10 to the negative 34 meters. I mean, just the magnitude of the order of magnitude. But for the electrons, when accelerated by a certain voltage, it can still exhibit the wave-like behavior with the wavelength about 10 to the negative 10 order of magnitude. Okay, so think about it. Can we find something with this small size in reality? In both microscopic world and macroscopic world, can we find that? Well, the smallest one we can think is about 1 atom, right? Or 1 electron. So the size of the atoms and size of the molecule, they can just be raised 10 to the negative 10, or slightly larger. So if we compare, let's say the base force, the Broglie wavelength is way smaller than the barrier. So that's why we can never observe the diffraction. But for electron, it's actually comparable, right? So that's why when the electron hits some atoms, it actually can diffract. Is that true? Well, the wave-like behavior of electrons has already been detected. So still, when we talk about the light diffraction, we get this pattern, right, through double slits. And also for electrons, we can also get a pattern, the diffraction pattern through a 3D crystals. And get this one. And this actually experiment was conducted by the 2 scientists. And because of that, de Broglie was awarded the Nobel Prize because his theory is actually correct, proved by experimental data. Okay? So in other classes, I think in advanced PChem lab, you will have the chance to talk about the diffraction pattern, but not for this class. Another advantage of de Broglie wave theory is it can expand the stable orbitals of Bohr's model. As I mentioned before, Bohr's model refused to expand that. But based on de Broglie wavelengths, we know all the electrons moving within the orbital must form a wave. So in order for the orbital to be stable, it must form the standing wave, like this case. Not this case. So this case is not acceptable. So in order to form the standing wave, we need to consider about the diameter of the circle and also the wavelength of the wave. So that's why we can't just have some solid number, have some discrete radius or radii for the orbitals. Okay, so that actually expands the stabilized orbital. But anyway, this just give you a just brief introduction. So there are some discussions in the textbook and also in lectures we talk about that. If you still have questions, we can talk about that afterwards. Okay. So any question about de Broglie wave theory? Again, particle wave duality. But how can we interpret that particle wave duality that give you a statistical understanding? So for a single particle or a small number of particles, the magnet exhibits the particle-like behavior. Okay, so 1 electron, 2 electrons, 3 electrons, 100 electrons, they're most likely like a particle. But when you talk about a large number of the particles, they behave like a wave. So if you talk about a larger number of electrons, they probably behave as a wave. Okay. This can be proved by, I think, the double-slit experiment. So if we only limited number of electrons go through the double slit, you get this picture, so this is random dots. But you keep increasing the number of electrons and keep detecting the point of the electron which hit the screen, you actually see the pattern. Okay, so actually from here to here, you'll see particle wave duality. They are both there. Okay, so next part, Heisenberg uncertainty principle is way more straightforward than the Broglie wave theory. So I just go over it very briefly. So uncertainty principles, for classical mechanics we know, simultaneously we can accurately detect the position and the momentum of a stuff. Right? Let's say we have a basketball flying, it's flying here, flying basketball. Then we can set up a coordinator. So by setting up the coordinator, we can easily give the location of the basketball, right? If we define the center of the basketball, is the location. So it's pretty easy. And we know it's moving within some certain velocity, so we can easily calculate the linear momentum at m times v. Which means, at the same time, we can determine the location, we can determine the momentum, or at least linear momentum. Like something like this. So if I but through a box, the same thing. So if we fix the time point, we can get the two things together. But this is not true for quantum mechanics or in microscopic world, where if the position is precisely determined, let's say here, we have a point here, and we set up a coordinator. So we can get the exact position of the particle, that's for sure. But in that case, you cannot detect the momentum. So the momentum could be different directions, could be different magnitudes. You don't know. Okay? But if your momentum is precisely determined, okay, like when I say moving along z plus positive z direction with a certain magnitude, I know exactly, then you don't know the particle space. The particle location. Everything is a blurred image. Okay? So that simply concludes the principle. The principle talks about microscopic world, you cannot simultaneously determine the position and the linear momentum. Okay? And based on that, we have actually one set of famous equation. So delta px times delta x, that means uncertainty in momentum on certain times, uncertainty in location is actually larger than some number.
So the deviation from precision of the momentum and precision of the location, is that due to the fact that these particles are so small that we can't detect them in any efficient way? Or is it because of the actual properties of the particle?
It's the actual property. We can derive neatly using quantum mechanics theories.
Okay.
And we will actually derive, I don't know whether the professor will do, but in the textbook, it actually derived it. Use quantum mechanics, start from Schrodinger equation, you naturally get this conclusion. It's the natural property for particles. Okay. So here I write two constants, just want to clarify. Some students told me, sometimes we use h bar, sometimes we use h bar over 2 pi, sometimes we use h2 with that. So which one I should use? So the answer is, well, either three of them you can just use. You use one of them, but in the exam, we will give you the equation which you will see which constant we will use. And you just keep the same thing using that. Okay. In your homework, that's fine. You use h bar, whatever. That's okay. But in the exam, just try to look for the equation and see which constant, okay, and use that constant. Okay. Another famous relationship is the energy time. So actually, the uncertainty of energy and the uncertainty of time also satisfy this relationship. Simply means the energy and the time cannot be simultaneously determined. Okay. But these are the two specific conclusions. I think in chapter 4, we're going to introduce you a more general conclusion that applies to all, and also includes this too. Okay. For chapter 1, we mainly introduce this one. Okay. So any questions about this? Well, so straightforward. So let's give you one exercise. Okay. A, B, C, D. Should be what? C, right? So keep in mind, it does not mean, uncertainty principle does not mean each individual one cannot be precisely determined. It talks about if we want to determine the two altogether, it cannot be. So it should choose. Okay? So I'll give you a fun picture. So the website wants to know your location, and the website wants to know your momentum. Oh, nice try. Yeah. So sometimes, not sometimes, in general, uncertainty principle also holds true for us. But the problem is, the uncertainty for us will be so small compared to our things. So let's say my height is about, give a number, 8 meters. Okay. But the uncertainty, I can calculate it. It will be 10 to the negative 98. Just make up any numbers. Give you the constant. So you will see uncertainty principle also applies, also true for me, but the uncertainty compared to the real value is so tiny, so we can just forget about it. So in that case, we say we can accurately determine your position. Okay? Just keep in mind that. Okay, so if no question, we go to the next one. Before entering chapter 3, actually I skipped chapter 2, which I will explain later. I will give you some clarifications for chapter 1. The first one is graph body is not always bad, right? As I mentioned last time. The second one is work function is not a function. Right? It's a form of energy. And the third one is electron volts is not an electron. It's a unit of energy. Okay, so I remember one student asked me in the lecture, said negative 3.6 eV. Does that mean we have 30.6 electrons in that orbital? Or not? It just simply means this is the energy of the orbital. And 1 electron volt is equals 1.6 times 10 to the negative 19 joules. Okay? This is just a unit. And I bet some of you still are not clear about the physical meaning of wave number. And we'll introduce you a new bead. What does that mean? The physical meaning of that. Okay? I'll give you a picture of the wave. In the physics, I know you're pretty sure. So this length is defined as wavelength. Right? And there's a frequency and the period of the wave. But here we talk about wave numbers. What does wave number mean? So I give you one box with a length of 1 centimeter. So let's say this picture. Okay. We use a box to cover the wave. So the question is, I want to ask you, how many wavelengths is covered or are covered by the box? How many wavelengths? 1.5. So this is a half. So there are 1.5 wavelengths within 1 centimeter, right? So the wave number is then 1.5 centimeter inverse. Well, that's the physical meaning of wave number. Simply means within 1 centimeter, how many wavelengths are covered here, okay? And putting a different unit, so centimeter inverse. And we introduced in class. So 1 over lambda is actually gives you the wavelengths, and you can also use the wavelengths to calculate the energy. Okay. All right, any questions about those clarifications? I hope you understand the physical meaning, and it will be more appreciated when using wave number. So wave number actually is directly proportional to energy.
Is it always 1 centimeter, or can it use meters?
You can use like meters, whatever. It's just then you can extend the box. But the traditional, the conventional unit is centimeter inverse. Conventional. Yeah, because most of the IR or visible or UV, they have like several hundreds of centimeter inverse. But think about if you convert to meters, you get a point something or way more larger number. So it's not really convenient. Okay. So then we'll go to chapter 3 actually. Why I skip chapter 2? So chapter 2, the first thing is it talks about classical mechanics. There's nothing new for quantum. And in chapter 2, we only talk about the derivation of the wave function, which we apply a lot of mathematical skills in differential equations. But for our class, actually we're not required to solve differential equations because we know some of you haven't taken that class. That's a whole mathematical subject about differential equations. So we just introduced some of the trees we played in differential equations and some of the conclusions we derive from that. We will cover part of it in chapter 3 by using Heisenberg theory. Okay, so through my sections. So that's why I decided to jump that. So chapter 2 is not that important. So compared to chapter 1 and chapter 3, chapter 2 is less important than the 2. Or actually way less important than chapter 1 and chapter 3. So instead of spending much less time in reviewing chapter 2, I suggest you to review chapter 3 if you have time. Okay. So chapter 3, at the beginning, we talk about operators. Actually, I'll talk about today. Okay, so we'll see. So first of all, what is an operator? Do you still remember that?
Tell us to do a function onto a function.
Tell you to do something. Right? Tell you to do something. It is a symbol which associated with some mathematical operation. So here, I mean, a mathematical operation, it could be this one, asks you to take the first order derivative with respect to x. Okay. Could be this one, the partial derivative. Actually, the second order partial derivative asks you to take that with respect to x, holding y as constant. I assume you reviewed some of your math, okay, from last section. I mentioned, starting from chapter 3, there'll be a lot of math here. It could be squared. Okay, 2 squared, 4 squared, 16. Could be square root, so take square root. But just a symbol without any number inside. Okay, if you're putting a number here, it's just a number. So operator is the symbol, is the operator in math. Okay? Or even if you rotate 90 degrees. So it seems like a geometric operation, but once we learn the groups theory, which we will not cover here, but in the inorganic chemistry class, when we talk about group theory, rotating can be converted to the matrix in the math. Okay, so it's still, in nature, it's still a mathematical operation. Okay? So all the steps here, they are defined as operators. Okay? So clear about the definition? So it looks a little bit weird first time, but after several times you will get used to that. Okay? Some important operators in quantum mechanics I want to list here. So later we're going to use some of them. So the first one is translation operator, or also called the location operator. So x with the operator with a hat equals x. It just equals x. The second one is potential energy operator. So V with a hat equals the potential energy itself. Okay. The third one is the linear momentum operator. It's not equals linear momentum anymore. It equals this first order derivative. And kinetic energy operator. But all the operators that are within one dimensional, and within one dimension, for multiple dimensions, we need more terms. But we don't care about that this time. We care only about within x directions. And finally, the total energy operator is by combining potential energy operator with kinetic energy operator, and will give you a Hamiltonian operator. And this is very important that we will use. You will hear the name many times after today's section. Hamiltonian operator. So here, you may be wondering why we call this as translation, or why we call this as potential, or why we call this as total energy operator. We will come back in chapter 4 and come back to talk about the physical meaning or the mathematical meaning of calling them as different energies. Okay. But here I just want to make a list, put it here, and store for future use. Some important properties of operators, which I think we did not emphasize quite in the lectures. I want to add it here. So operators are not always commutative, okay, which simply means you cannot always change them. We know the multiplication is commutative, right? 1 times 2 equals 2 times 1. But for operator, 2 together, you cannot switch their position. Or at least you cannot always switch them. In some cases, you can. So if the two, you switch the position, it still be the same operator. We call A and B operators are commutative, or we say the two commute. And we will have some important conclusions derived from here in chapter 4. But here I want you to know the basic definition of commutation. Okay. Two operator commute simply means they can switch position. A second one is operators are not always associative. So if you have A, B, C together, it's not always equal to A, B together and then C. So this is totally different from the numbers or from the multiplications you learn in the math. It's totally different. Do not try to switch the position. Do not try to combine with different parts. And operator with a function like we showed in class. So how do you read that if I ask you to read this? A operator times function, right? Naturally you want to think, because we have a times fx, you also expressing this way. Well, if you read it that way, you completely misunderstand the meaning of an operator. So this way that a operator operate on the wave function. Sorry, not wave function, the function. So here I want to emphasize is operate on does not mean multiply. So simply means a operate on fx is not the same thing as a the operator times fx. If you are not clear about this, you will end up with this conclusion. So Schrodinger equation tells you a Hamiltonian operator operating on wave function equals e times wave function. All right, wave function, we cancel them, and you end up with the conclusion that Hamiltonian operator is inert. That operator is inert. Hamiltonian operator is a bracket of a lot of terms, right? It's not inert. So what's wrong with this? Because from this derivation, you assume that's totally wrong, okay? You assume that h operating on phi equals h operator times phi, which is not true. So when you see this symbol here, the two actually, they are one identity. They cannot be separated. So you cannot split them through here. Okay? They are two together, they're one thing. This is the one actually, one function. Right after operation, here a new function. This is the whole function. How can you separate the function from the middle? Okay. I want to be clear about this, very clear about that. Okay, and don't try to think about it that way. Okay? That will confuse you a lot. Another proper case is when you evaluate the operators, and in this case, so you have a lot of multiple operators who operate on the same function. So when you do the calculation, instead of from left to right, in this case, you're from right to left. So from G to E. So simply means you first evaluate G operator on Fx, give you 1. And then E operator on the whole thing. Sorry, F operator on the whole thing. E operator on the whole thing. B operator on the whole thing. So go from the right to left. Okay. So never go from here. So this is another property. And this one is coupled operators. So for example, we can combine two operators together or multiple operators together and give you a new operator. So let's say this is a linear momentum operator, right, expressed in this way. And we can combine another linear operator together by square it. And you should be able to evaluate what the new operator is. Okay. So let me show the derivation here. Without showing it. So just step by step, so you will understand how to do the calculation. So the Px defined as IHR. Right? Okay, so square it. So the whole thing gets squared, right? So the first one is we have some coefficient before the operator, so we can first evaluate this part. So minus I squared equals what? I squared equals what? Negative 1. So I minus I squared 1. H bar squared H bar. Right? With positive 1.
Why wouldn't it be just I squared instead? How do you keep the negative symbol there?
Oh, so it's not. Okay, let's get in. Yeah, you are right. It's actually this. Right? It's actually this. So should we what? Pay attention. Very easy to make this negative H bar squared. Okay. You get an idea? So negative I squared equals I squared equals minus 1. Okay, yeah, great. So this is the coefficient part and the operator part. So first order derivative squared will be the second order derivative. So that's actually the new operator. Okay. Well, in your homework, which we'll post today, there's one similar questions like this. Okay. So you do it, you get a new operator. So the second order derivative sometimes can be denoted as this. So you take the first order and then you take another first order. The same thing, just different notations. All right, any questions? I know it's time to review your math, okay? If not, I have two important properties or conclusions for operators. The first one is you should be able to tell whether the operator is linear or not. So you should be able to tell whether the operator is linear or not. How can I tell? Just one way, only the way, by using the definition. So linear operator is defined as this. So let's say if we want to check whether the Q operator is a linear operator or not, we use a Q operator to operate on this function. So this function contains two terms. The first one is one function times a coefficient, arbitrary coefficient, arbitrary wave function, not wave function, sorry, arbitrary function, times another arbitrary coefficient, times again another arbitrary function. So if the left-hand side can be successfully converted to the right-hand side, then this operator is called linear operator. Okay. We showed one example in the lecture. Exactly this one. This one is a linear operator. Okay. Let me give you one simple example. So let's say we have an operator means plus. Okay. So the Q is not plus. It's not a bad example. Well, let's say E over dx. This is the QR operator. So whether this is a linear or not, so you operate on the thing is A F1 plus A2, A1 F1, A2 F2. Okay. So we're plugging the operator will be this one. And this give you what? A1 dF1 dx plus A2 dF2 dx, right? And what is this? So this part is what? Q operator, right? Agree? So similarly, right, satisfy the requirement for linear operator? Yes. So because of this, Q operator is a linear operator. Okay. So in our homework, we asked you to show your reasoning. That simply means show this process to check if this one equals this one. If someone you get a derivation, blah 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 blah, and you find these two are not the same, then they are not linear operators. Okay. Any question? Usually there will be a question in the exam or in the quiz. They ask you to tell.
So, even in the book, is there an example of a non-linear operator that's like simple, like to sort of see what it would look like?
Well, I do not guess to use any shortcut. The easiest way or the safest way to use the definition. So always use the definition to check. Some of the operators are pretty straightforward to tell.
Okay.
Yeah. So every question will ask you whether it is linear or not. Go back to the definition and show the derivation, and you will get the 4 credits if you are correct. You must be correct anyway. Okay, so linear operators, and the second one is eigenfunction eigenvalue. It's even more important than the linear operator. Okay. So eigenfunction eigenvalue defined as this situation. If we have an operator operate on a wave function or a function, which will give you a constant times another function, and if the two functions they are identical, then we call the two functions here. They're actually not two; they're the same. The one